Well, thank you for the invitation. It's really great to be here. I'm thrilled to be at this conference. So what I thought a long time, what should I talk about? And in the end, because I think this conference has already a long history and it spans several functional programming languages, I thought I'd do something of a more general interest, not just for Scala programmers. So I'm talking about implicits. Well, you will say, well, implicits, isn't that a typical Scala feature? And indeed it is, but I think implicits are something that also exists in a lot of other languages. So, just, let me see. No? Yeah. So let's start with an empirical study that is coming out in Uppsala later this month, in next week, I think. Scala implicits. The authors conclude they're everywhere. So they essentially mined 7,280 Scala projects, 18 million lines of code, 8 million implicit call sites, 370,000 implicit declarations. And they concluded that 98% of all projects use implicits, 78% of projects define also new implicit definitions, and 27% of call sites are implicit. So they're really absolutely pervasive. So you could say, and you would be right to say, implicits are Scala's most distinguished feature. But I believe they're also its most controversial feature. A lot of people had problems with implicits at some point or another, and there's a lot of angst and hate about implicits. So let me just take this. So an alternative title of this talk should be Mistakes I Made When Designing Implicits. So I sort of had a long talk with myself and thought about what went well, what didn't go well, how can we do things better. So what this talk covers is some historical perspectives. We're going to go back in history a little bit, and I'm going to show you how implicits became what they are today. I'll talk, frankly, about some design decisions that I believe now turned out to be mistakes, and I'm going to show you a redesign of implicits, which is essentially the biggest thing that will change for the upcoming new language of Scala, Scala 3. So if you look at the history of implicits, then they actually had a fairly strange way to come about, because the first thing that happened was implicit conversions, which actually turn out by now, in retrospect, to be also the most problematic thing. So in 2004, we had the first version of Scala with maybe 10 users worldwide, and it already shipped with implicit conversions. Why did the language have implicit conversions? The motivation was to solve the so-called late extension problem, which was a fairly burning problem for object-oriented programming at the time. So the problem was that you say, if you have a class C and a trait T, how do we make C extend T after the fact? So without changing the code of C. No code changes to C are allowed. And at the time, it wasn't clear what a good solution would be. So I came up with a pseudo solution in quotes, to say, well, we can't really make C extend T after the fact, but we can essentially implement an automatic wrapper conversion, and that's how implicit conversions were born. So here we have a function, C to T, that takes a C, gives me back a T, and it basically just creates a new T with the right method implementations that we have here. And by virtue of this keyword implicit, we get the conversion is applied automatically. The compiler will apply it if a method of T is demanded, but a value of class C is found. So this, as you can imagine, is very, very powerful. It's also easy to abuse, but hey, with 10 users, who cares? So at the time, that wasn't really a major concern. Then, 2 years later, Scala was still a tiny language, came the second step, which was implicit parameters. So the idea there was, once you have the basis of implicit resolution, that you somehow can go out and find implicit things, it's tempting to also do implicit parameters with it. The delta is actually relatively small, and with that you get type classes for free. So let's take a trip back in history, and I show you some slides that I presented in July 2006 at the IFIP WG 2.8 working group. That's the working group for functional programming. So the title of the talk was Poor Man's Type Classes, and that's basically how implicit parameters were born. So the intro slide said, type classes are nice. A cottage industry of Haskell programmers has sprung up around them. Should we add them to object-oriented languages, specifically Scala? Object-oriented languages, so that's what Scala was at the time. It wasn't really meant, well, it was sort of intended to be a fusion of object-oriented and functional, but functional programming language were really nowhere in 2006. So it was really, the main idea was it's an object-oriented language which has some functional features added to it. Okay, so the argument goes further. It would be conceptually pretty expensive to add a new thing, and we already spent the keywords type and class, so there's no room for type class. But then there was the observation that type classes are essentially just implicitly passed dictionaries. That's how they're implemented. And dictionaries are records, so essentially objects. And we don't want to duplicate that. So the idea was, let's just concentrate on the delta between object-oriented records, objects, and type classes. And the delta is really just this implicit passing of big dictionaries. Hence, implicits were born for parameters. So the basics of implicit parameters as presented then in 2006, you recognize this code today even still. So, well, we just have this implicit parameter here. We have a sum over monoids of some type parameter A, and well, that's essentially a simple definition of it. Okay, we can combine normal and implicit parameters, and if there's only one implicit parameter list, it must come last, which is another restriction that we would like to lift by now. Okay. So implicit can then also be used as a modifier for definitions. So I can write implicit objects and like string monoid and int monoid. So then I have monoid instance for ints and strings. And you saw that in 2006, actually, we still wrote int with a lowercase. That's another thing that changed. And that means that arguments to implicit parameters can be inferred. So we just write some list 1, 2, 3, and that's really some list 1, 2, 3 int monoid. That's the thing that got inferred. So, okay. And now comes the fine print. Now come the rules that I want to just go through them because it turns out that these rules caused us quite a bit of trouble afterwards. So the rules are actually very simple. It says if an argument for an implicit parameter type is missing, so not given explicitly, it's inferred. An argument is eligible to be passed if it is itself labeled implicit, okay. Its type is compatible with T, okay. And one of the following holds. Either the argument is accessible at the point of call by a simple identifier. So there's a simple identifier, a name, that names the argument. And ways that it could be accessible would be it's defined in the same scope, it's inherited, or it's imported. Or it's defined as a static value in some superclass of T. So today we would say as a value in the companion object of some class. Okay, if several arguments are eligible, choose the most specific one. And if there's no most specific eligible argument, a type error. So this thing here, that I just want to draw your attention to this phrase here. So the implicit argument must be accessible at the point of call by a simple identifier. So that turned out to have fateful consequences. Okay, the other thing was about locality. So a consequence of implicit argument resolution is that one can have several instance definitions, so no global coherence, and there are some rules to keep local coherence, to keep things under control. And one thing which is very important is essentially when you pass a partial function, a function that is not yet fully applied, do you pass the implicit arguments where you create the closure or where you apply the closure? So there's a choice with it. And Scala came down firmly at the point where you create the closure. So here it says, implicit parameters instantiated where a method value is eliminated, either applied or converted to a function. That is actually in contrast to implicit parameters in Haskell, which are not exactly the same thing as type classes, where implicit parameters in Haskell are considerably more ambiguous on this point, which is one of the important differences between implicit parameters in Scala and in Haskell. Okay, and finally, there's a way to do there was a way already to do conditional implicits, which is just an implicit def, like the list monoid here, that takes another monoid of the type parameter as an implicit argument. So that way you could get conditional implicits. Good. So that was sort of the flashback of what happened in 2006. In retrospect, let's maybe first concentrate on things I believe we got right. So I believe we got right the idea that type classes are types and dictionaries are values, that we don't want to have another concept, another level of things of essentially shapes of types that are type classes or things like that. I think it's actually much simpler to say a type class is a type and a dictionary is a value. And I also think it's very important and very useful to have that instances can be defined anywhere and that local instances are possible. So that means no global coherence. I know that there's a big debate, pros and cons, so I'm firmly on the side that we want to have multiple implicit definitions and we do not want to pay for global coherence. And I believe the other thing we got right was this relationship with eta expansion, that implicits are passed in the expanding context. So when a closure is created, the closure basically gets all the implicits at the point of creation. That, I think, was another thing that we got serendipitously right at the time. But now to the mistakes. So I believe the first mistake was depending on names. So implicit resolution was defined as finding a unique name. So I recall this thing in the spec that I underlined in red. One of the following holds, X is accessible at the point of call by a simple identifier. So this is very concise, very elegant from a spec point of view. Just one phrase and you're done. Basically, that's what explains everything. But it has unfortunate consequences for programming because now names matter where they shouldn't and shadowing is a problem. So here's an example. Let's say you have an implicit value A of some type class and you want to summon it here in this F, but F happens actually to have a parameter that's also called A. So now actually the previous spec forces implicit resolution to fail because it says, well, here I cannot synthesize a simple identifier. I could try A, but the A means that A here, not the implicit type class. So the compiler is forced to say, no, I can't give you an implicit there. And technically, this thing is a so-called shadowing error. And there's really no reason, I mean, why that should be. The other side of the coin is also problematic, and that is that essentially, since it's just all about names, nesting of things does not matter. So this thing would give an ambiguity where we have a value A of the type class TC, and then we have an implicit parameter EV of the same type class. And we summon TC. In this case, it wouldn't get the innermost one, the EV, the parameter, but it would give you an ambiguity. It would say, well, I can synthesize this as A, or I can synthesize this as EV at the same type, so I don't know what to do. It's an ambiguity. So that's also problematic, in particular because it causes hairy problems for coherence. And with coherence here I mean local coherence. Local coherence is essentially the thing that the compiler gets confused and says there's an ambiguity when there really isn't one. And you try to convince the compiler that, no, it's okay, there is only one instance. So let's run an example. So let's say we have the typical thing of a hierarchy of a functor class with two subclasses, monad and traverse. So they both extend functor, but they don't extend to each other. And then there's a map function that's defined on functors. And now we have a function f, which takes a type constructor, capital F, which is both a monad and a traverse. That makes sense. And we want to call map on it. Now the compiler would get confused and say, well, basically this context bound here says, give me an implicit instance, an implicit parameter for monad, and here it says, give me one for traverse. So these are parameters. You can think of them as additional parameters for this function f. And the compiler would say, well, now I have a map for monad, and I have a map for traverse. I don't know what map you mean. I said, the answer, of course, it doesn't matter. They're both extend functor, and it's that map that you should take. But the compiler doesn't know that. So it would respond that that's an error which is ambiguous. That's the local coherence problem. So one might be tempted to say, well, sure, I mean, there's situations where the compiler gets confused, but we can teach the compiler what we mean. But let's just do essentially a local definition which says, well, we have a functor, EV, and it's actually the monad instance. I don't need the traverse instance. I mean the monad instance. Sure, they're the same, but I just have to convince the compiler, well, just take this one. Don't take the other one. So does that work? No, it doesn't work. It's still ambiguous. Actually, now it's ambiguous in one more way than the others. So now I have the monad parameter, the traverse parameter, and the nested EV parameter. So now it's ambiguous in 3 ways instead of 2. So that didn't work. And it doesn't work because nesting is not significant. OK. So another problem that is sort of more a usability problem and less sort of a principal problem is that the syntax is dangerously close for concepts that should really be quite different. In particular, when if you look at implicit conversions, which, as I said, were the start of implicits. So that thing here is an implicit conversion. It's just implicit for a thing that maps T to U. And that thing here, it looks almost like a conversion, but it's a conditional implicit. So it says, well, I can synthesize a value of type U, provided that there is an implicit value of type T. So these two are used in completely different ways. So one is a conditional implicit, the other is a conversion. One is sort of everywhere, the other is quite problematic. Yet the difference is a single, essentially, keyword implicit, which furthermore is used in lots of different circumstances. So that's problematic. Another thing that's problematic has to do with the role of implicit parameters, which are also too close to normal ones. So as the example I show you here is, there was this rule which says, okay, an implicit parameter can be supplied with a normal argument, and if no normal argument is given, the compiler will synthesize one. That's basically the rule. But there's a problem in this case here, where you have a function f, and it takes an implicit parameter of type t, and then it goes on and is a function from type u to v. So you might want to apply f to a u argument, but you can't, because that thing here, that u here, will actually count as the argument for this t parameter, for the implicit one. Compiler will say, hey, that's an explicit argument that fills in for this implicit argument. So that would give a type error. You can get around it. Essentially, you have to say f.apply u, and that would force you to be the function, and that would force the argument to be passed. But hey, that's ugly. That's essentially a leaky abstraction that we force on users. So basically, the fundamental problem here that became apparent only in retrospect really was that if implicit parameters are different, so should arguments be. So implicit arguments and normal arguments should be syntactically different. We sort of cut one corner too many to say, well, they're just the same. That actually leads you into problematic situations like this one here. Okay, and the final mistake, and afterwards I shut up about it, is that the implicit scope is also too implicit. By that I mean that essentially the implicits, they are in your program, and the question is, where do you get them from? Where are they? And I believe that we have a limited implicitness budget, so we should be pretty sure where these things are coming from. I don't for instance, believe it's a good idea to say all implicits in your program somehow can fill in for these things, because that means that basically you have to know what your program is, and your program can be huge, and your program can change all the time. So this is something very dangerous. In Scala, that's not the case, so you have to import the implicits that you want to use, or they're defined with the types. But even the imports, they are a bit too silent, and in particular, if the import is a wildcard import, which it is mostly for implicits. So a wildcard import just wholesale imports all members of an object or a package or whatever, and it imports normal members and implicit members. Why is that problematic? Well, you can't really see what implicits your code uses. These wildcard imports, you typically have that, you have a bunch of them, and an crucial implicit definition could hide in each of these definitions. That's bad for understanding where the implicits in your program are. While you could say, well, maybe an IDE can help you. You can like hover, and it tells you what kind of implicit arguments it has found there. But it's probably even worse when you do not have the right imports. So essentially, there are these. Program A works, and there's a long list of imports. You try to copy it. You forgot one of the imports. Nothing works because your implicits are not found. So that's very, very frustrating. The other thing that's not good about it is that it really encourages abuse. There's a lot of people who love to just essentially arrange things so that they tell you just should import my library, _, and you have everything. Your whole world changes. But I believe while it's cool for library writers to have this additional power, it's not so cool for end users of those libraries, because they don't really see what's going on here and what comes with my library, _. Okay, so that sort of staring in the distance is about it, to say that we have sort of certain things that work, I believe, and others that are problematic. What we can take from it is to say, well, that implicits, they sort of came about half by accident. They started as a way to express conversions and to extend classes after the fact. And they got generalized to provide type classes, extension methods, and many, many other things. The mechanism itself is impressively flexible and useful. So I think what I like about implicits is that essentially they give you the raw power of these things without coating that in a lot of sugar or things like that. So it's really sort of what goes on underneath, and in implicits you have that directly. But on the other hand, that mechanism tends to hide often the high-level intent and the overall architecture. You get too drawn into the actual mechanics of what is passed implicitly where, and that can be a problem. So Scala 3 is a new version of the language that is going to come out next year. It's, I think, the biggest redesign since the inception of the language. One of the important things is that it's built on, by now, well-researched foundations, namely the dot calculus, and it has an emphasis on accessibility and safety. The timeline is we're right now close to feature freeze. We expect the first stable release in 2020, and the language as it is currently is evolved in the Dotty project. Dotty is essentially the research prototype, but the Dotty compiler will become the Scala 3 compiler next year when we release 3.0. So Dotty is a long-running project. It's been elaborated over the last 6 years. So there's a lot of stuff in it that will come out next year. But I believe the most important redesign is really implicits. So there are a lot of other good things in there, but implicits is sort of the most drastic step because it changes also a lot of what exists currently in the language. So let's take a big step back and revisit implicits. So what is it that we really want to do with them? And the core concept really is we want to infer terms. We want to infer values, not just types. We are all used to type inference, but implicits infer the term that for a given type. So the motto is trait types for terms. your programmer gives or infers a type, and the programmer gives a type, or the compiler infers it, and the compiler produces a term that matches that type. So this term synthesis is the essence of implicits and type classes and all these related things. So what we want to do is really emphasize this idea and focus on it. So instead of adding implicit as a modifier to many, many different things, changing the meaning of each in slightly different forms, we want to have a single construct that does this, that introduced a designated term that can be inferred for a type. And we call these terms given instances or just givens. So given is the new implicit. So given instances. Here's a first introductory example. It's sort of the one that we mostly start with when we do type classes. We want to explain what orderings are for ints and list of t. So here's a trait, ort. It has 3 methods, compare, less than, and greater than. So that is essentially another new thing in Scala 3. We can write extension methods like that. So we just say this method is applied infix, and that's the left argument, and that's the right argument. Okay, and now we say, well, we want to have 2 instances for orderings. Integers are ordered and lists are ordered. In both of these cases, we have to explain what compare is, because compare is an abstract method here, and the other 2 are already implemented. So for int ort, we have the usual compare that you see here. And for list ort, we have a slightly longer compare that I have left out. But the important part for the list ort is, so list ort works for any t for which there is an ordering of t. Of course, that's the conditional implicit. And then if you have an ordering of t, you can construct an ordering of list of t. And that's what its compare method is. So you see that whether it's conditional or not, previously it was like an implicit object or an implicit def or an implicit class, and all these things had to be constructed in a very subtle way. Now it's just given. You say what? You say we have a given instance for a given type, and then we explain essentially what's missing, and that's all. The other new thing is that the names of these given instances can also be left out. So you can also write it like that. You can just say, well, here there's a given ordering of int, where that's the compare method. And here you say, for any t that itself has an ordering, is ordered, there's a given ordering of list of t, where the compare method is this. Because the names, after all, of these things, they don't matter, because you will usually not refer to these things. The point of givens or implicits is that the compiler will produce them for you. So why should you bother give them a name? There could be reasons for giving them a name, of course. The main reason is really binary stability. That you want to say you do not want to rely on compilers inferring names and maybe inferring different names in different versions. That way you can essentially nail down a name as a programmer. So for long-living APIs, that actually makes a lot of sense. But for doing things quickly, you should be able to leave these names out. Okay, so those were given instances which essentially, if you translate them to what happens, so this would be an implicit object. So essentially, you write the dictionary, and that would be essentially a function that produces a dictionary given another dictionary. You can also write them as aliases. So that's another thing that often happens for context passing. So for instance, a lot of the concurrency abstractions in Scala futures and other in Scala parallel collections, they need an execution context, and it's very boring to pass an execution context down to everything. So it's an implicit, and the way you can write this now is you say, well, I have a given global execution context, and that's a fork join pull. Or I have a given position, and that's the enclosing position of the enclosing tree, and so on. So these things can be aliases as well. The point is, compared to previously what happened, is that you give up control of how the compiler implements these things. Of course, there are rules, and you can read them up, and it's actually, if you think about it, it's fairly obvious how the compiler will implement these things. But the point is sort of a change in viewpoint. You as a programmer shouldn't have to worry about this. You as a programmer should worry about saying, I want to provide a given instance for a type that can be inferred by the compiler, and here are the bits that essentially I need to fill in the undefined pieces of that type. And how that comes to pass, hey, I mean, that's the point about implicits, right? That they are implicit and the compiler will pass and construct them automatically for you. Okay, so let's have a look at the parameter clauses. So they actually look a lot like implicit. So here you could say, well, just replace given with implicit, and you have the old syntax. So here we have a max method that takes an x and a y, and it takes an given ord parameter, and it uses this ord in the compare thing, right? And then you can call this, of course, as before, as usual. You can just leave out the given parameter, it gets inferred for you, or you can write it. But if you write it, you must repeat the given. So that's a big difference between implicit and given. If you write it with an implicit, Okay, now let me just go on with this thing. So you write it like this. So you write given int ord, given list ord, or since list ord is itself parameterized, you can go one level further down, and now you have to have specified it completely. But you can't write it like this anymore. So for implicits, this is really washed out. That's a great effect given that it's now illegal. The red thing, very very well done. It's clear on my screen, but on this one it's washed out. But it should be washed out because it's actually not legal anymore. So it's not legal because you have to match up the parameters exactly. So you have to put the given in here. And that's sort of also the hard reason why we couldn't name these things implicit. They had to have another name because the rules have changed between arguments and parameters. If we had named them implicit, it would forever be ambiguous. Do you mean the argument for this or not? So that's why we changed for the parameters the syntax to given. Also, I think given is a nicer name because it gives you something that essentially it's positive. It says there's a thing that's given in the context of this program rather than saying there's an implicit object or there's an implicit function. If I write an implicit object, that object is not implicit. It's just as explicit as the next object. But what I mean is it's a given instance for if you want to infer the type, then that object is available. Okay. So let's see how that works for type classes. So we had this semigroup monoid example in the 2006 thing. How would that look now? That's essentially what we have. We have the trait semigroup. We have a monoid, which is a semigroup with a unit value. Semigroup has a combine, which is an infix extension method. And now we can have an instance like monoid of string, and we give you essentially the two implementations of the two methods, of the combine method and the unit. And then we could have a sum method that works for all t's that have a monoid instance, and it sums essentially all the elements of a list of t. So that would be a fault, and we start with the unit value of the monoid, and we combine with combine. So that thing here, the summon method, gives us essentially the given instance for the type that we specified here. So you see it's actually a very quiet and nice syntax for type classes if you compare to what you had to do now. It's much, much nicer, in particular in the way it treats infix methods. So far, to do this in any way that's reasonable, you needed essentially a macro package called simulacrum, which would essentially add a bunch of imports to your program and sort of to make this work in a way. But now it's available much more directly and much more robustly. Okay, so this summon method that I've shown here, that's essentially the new implicitly. So summon is just written like this. So summon is a method available in predef, the standard definitions that are automatically imported into every module. So summon of t takes a given parameter of type t, and it returns just that parameter. And that's all there is to it. Good, so that's the core of it, given instances and given parameters. Let's look at the remaining bits. So one question is, well, implicit started with conversions. What about conversions now? Should we just drop them completely? I don't think that would be possible. I think in some way there are always some needs for conversions, but we shouldn't make it so obvious and simple to write them. So one of the problems with current implicit tutorials is, since sort of conversions are the most concrete and obvious use case, most of the tutorials start with conversions, where you say, no, don't do that. Conversions are actually very problematic in most cases. Sometimes you need them, but you shouldn't just essentially open the doors wide and say, invite everyone to do conversions. So what the rules are now is to say, well, conversion is essentially just a special type. And you can define given instances for these conversions, and then you get the implicit conversion. So instead of having an implicit def that's a conversion, we essentially can give you a given instance for a conversion class, so Scala.conversion, from string to token, and we essentially have to give you the apply method that converts a string to a token. Or you could use an alias given like that. The two are equivalent. So the second one is just says my conversion from string to token. It's actually this partially applied keyword function. So that's how we do conversions, and that means conversions are treated rather than as a feature by itself, they're treated as a special case of the general given instance design. And the last thing I want to cover is imports. So for imports, we had this problem that we say, well, wildcard imports are really too powerful. They pull in too many things. So what we will do now is that we need a special import selector to import givens. So here I have just a simple class. Oops, yeah. So it's a class and a TC and a given instance and a normal function, and I have an object B that essentially has two imports. One is a wildcard import, and that wildcard import would only import the F here. And the other import A.given, so I use given now as an import selector, would import the TC. So given essentially says import all given instances in the selector. The advantage is you see it. You see it in the import list. It gets syntax highlighted. You say, OK, here's somewhere given instances get imported. OK, you could say, well, yeah, but that's still not so good because it's still a wholesale import. And the answer is, yeah, well, you could import them by name, but then you say, yeah, but what if these things are anonymous? Then what's the name? Well, there is a name that is actually specified, but the name is long and you don't want to type it out. So what do you do? So there's a new way of import, which is, I believe, quite useful to say, well, what do we care about when we import given instances? We care about not about their name, we care about their type, right? We want the given instance for this type. That's a good specification. So we want to say import instances given essentially what you have for the ordering, any ordering instance we want. So that you write here, given ordering, the underscore here is the abstract type of ordering, and that would import int ord and list ord. Or you can mix them and you can say import instances I import by name and the given execution context. So that would import IAM and EC. So that's a much more precise way to specify what imports are and where you get them from. There are also many, many improvements in details. Given instances and parameters can all be anonymous. Nesting is significant, of course. Shadowing is eliminated. We restricted the implicit import scope, took away some of the things where it was surprising that an implicit instance was available. There are more robust rules for implicit prioritization and better error messages. Okay, so that's essentially the big package that we have in Scala 3. The hardest thing actually was naming them. So the design that I've shown you has been fairly stable, not 100%, but let's say 90% for the last 9 months or so. But how do we call these terms that get inferred for types? And we went through an impressively long list of names. So here you have the essentially, I think that's an exhaustive list of everything we tried with an actual prototype implementation. Witness, evidence, instance, wrapper, implied, assume, keep implicit, delegate, or representative. But in the end, given had the broadest support, so that's what it is. Good. So migration. So if you use Scala 2, maybe you're scared now and say, oh, so many things are changed. And indeed, implicits are everywhere, like we see 98% of projects have them. So what do we do? Well, current implicits are actually still supported in Scala 3, or will still be supported in 3.0, and will probably be deprecated from 3.1 on, but deprecation doesn't mean take away. So they could actually stay a long time. So essentially, we want to gently nudge people to use the new givens and to get rid of the old implicits, but we're not in a hurry to do so. There will be automatic rewrites that help you do that, and there are also provisions that are made for cross-compilation. So in particular, those two things are important. The first is if you have a given argument, so you write in an argument list given foo, that also works for old-style implicits. So that means that you can use that for old-style libraries and new Scala libraries. For implicits and givens, you can already starting with Scala 3.0 to use given for your argument to make clear that, well, that's actually an argument for an implicit parameter. And the other thing is that if you have an import with a given specifier, that also works for old-style implicits. What that means together is that programs, applications, can already migrate to the new style without necessarily all their libraries having migrated before. So the libraries could still use the old implicits, but you can use them as if they were already the new givens. And that also means that at some point in the future, when most of the ecosystem has moved over to givens, then essentially the remaining libraries can move without a large cost. They can just at that point decide, okay, now is the time we switch and change to the new givens. So that allows to migrate user code before libraries are moved over. And you can try it out today. It's at .epfl.ch. Thank you.